Welcome back to the deep dive. Our mission here is to take the most complex, high-stakes technologies that, really prop up the modern internet, drill down into the core data, and pull out what really matters. And today we have an incredible case study. It's this amazing contrast between absolute digital fragility and, on the other hand, the most profound depths of cryptographic security. We are going deep on a recent catastrophic failure at one of the internet's most foundational layers, Cloudflare. We're dissecting their November 18th, 2025 outage, which, Cloudflare itself came out and said was its worst systemic failure since 2019. This was the day the internet didn't just slow down for a huge number of people. It just stopped.
And it's so crucial to get the scale here. Cloudflare isn't just a CDN anymore, not by a long shot. It operates as the virtual immune system for huge parts of the modern web. It's the infrastructure that's accelerating and protecting everything from these massive corporate sites all the way down to small e-commerce shops. So when their core traffic fails, it means DDoS protection is down, authentication gates are completely locked, and global HTTP traffic just stops flowing. The failure really exposed a monumental degree of operational complexity.
And the context of why it failed is where the story gets truly bizarre. We're not talking about some massive, sophisticated nation-state cyber attack, or a submarine cable getting cut, or a fire in a data center, nothing like that. We're talking about a cascade triggered by a single, seemingly harmless database permissions change.
That's the initial frame you have to grasp. It was the ultimate real-world demonstration of the butterfly effect in a huge distributed system. For almost 4 hours, core services were just crippled because engineers who were trying to make the system more reliable and secure inadvertently put a poison pill into the configuration pipeline. It was just a single bad piece of data that weaponized a previously harmless query. Okay, so let's unpack the sequence and see exactly how that data went rogue.
All right, let's start at the very beginning then, the trigger. What were the engineers even trying to achieve when they kicked this all off at 11.05 UTC?
Well, the intent it was actually really sound. They were focused on reinforcing security within their massive ClickHouse database cluster.
Which is used for what exactly?
It's for large-scale analytical querying. So they were updating their permissions management. Specifically, they wanted to make sure that these things called distributed subqueries, which let the database spread complex tasks across a bunch of machines, ran strictly under the initial user accounts. The goal was just better reliability, better security, basically finer-grained control.
So they were trying to harden the system. A good thing.
A very good thing, in theory. But that hardening effort, it just immediately backfired.
Okay, walk us through how that happened. How does a security improvement become a system killer?
It's a classic case of an implicit expectation meeting an explicit new reality. So inside this ClickHouse cluster, they have different logical databases, schemas. And when users, or in this case automated systems, query the system tables to get metadata about columns, they usually only see tables in the primary or default database schema. But the actual raw data storage tables, where the data is physically written for logging and analytics, they live in a separate database schema. It's often called R0.
So the query had always been sort of implicitly accessing data in R0, even though it was only supposed to be looking at the default tables.
Not exactly. The user accounts already had implicit permission to access the data stored in those R0 tables. What the engineers did at 11.05 UTC was make that access explicit. They basically just told the system, yep, this user can definitely see their R tables now, along with everything in default.
And that one small explicit change had a huge immediate side effect on a piece of code that was already running.
Precisely. And that gets us to the unintended consequence, the duplicate data. There was this critical pre-existing query used by Cloudflare's bot management system, and this query was designed to get column metadata to generate a configuration file. But, and this is the key part, the query did not include a filter for the database name. It just asked, show me all the column metadata.
Ah, so before the change, it only got one set of results.
Exactly. Before 11.05, because the R0 schema access was implicit, the query only returned metadata from the default schema. You got a clean, concise result. The second that R access became explicit, the query suddenly returned column metadata from both the default and the PEL schemas at the same time.
Wait, so the underlying data didn't change, the query itself didn't change, but just because the system now explicitly knew about both schemas, the result set just doubled. That's remarkable.
It is. A single permissions flag turned a normal query into a data explosion.
And a postmortem said it was even more than doubled, right?
Yeah, it effectively more than doubled the number of rows returned, which resulted in all these duplicate column metadata entries. And this This bloated query response then became the core input for a critically important process, generating the feature file.
Okay, let's talk about that feature file. What is it, and why is it so vital to how they route traffic?
The feature file is really the backbone of their bot management machine learning model. You can think of a feature as a specific characteristic like a user agent string or a request rate or specific header patterns that the model uses to tell human traffic apart from automated bot traffic. This file, generated from that Klitschhaus query, gives the software on the network machines the parameters and weights to, score and handle incoming requests.
So if the source query results doubled, the feature file basically got stuffed with duplicate entries for every single trait the system was tracking.
Exactly right. The weaponization of that file began immediately. This oversized file, full of duplicate feature entries, was then distributed across their entire global network of machines that handled traffic routing, the core proxy services. This all started around 11.28 UTC.
And this is what leads directly to the Rust panic. For anyone who's not familiar, what does a panic actually mean in a system like Cloudflare's core proxy?
A panic in Rust is. It's not a graceful failure. It's not an exception the program can catch and recover from. A Rust panic means there has been an unrecoverable internal consistency failure. It's a catastrophic error where the program realizes one of its own strict rules has been violated. In this case, it was a heart memory boundary violation.
And they had that boundary set for performance, right?
They did. The bot management module inside the core proxy had a pre-allocated memory limit for these features. And that's super common in high-performance networking. You pre-allocate exactly the memory you need to avoid the overhead of allocating it on the fly, which makes processing way, way faster.
So what was the limit, and how far over did this bad file push it?
The limit was set to 200 features. And based on historical data, that should have been plenty. Normal usage was usually around 60 features. So 200 felt like a really safe, generous ceiling. But the duplicate entries in that configuration file, from the query doubling its output, immediately pushed the number of features well past 200. It just blew past the pre-allocated buffer. When the software tried to load that oversized file into its fixed memory space, it triggered that internal consistency failure, the catastrophic Rust panic, and the core proxy service just died.
So the system wasn't crashed by a flood of malicious traffic, but by its own internal data being slightly different, a piece of metadata being exposed. It's almost poetic in its complexity.
And that's what led to this agonizing, oscillating crisis. Because the bad configuration file was being generated every 5 minutes from this ClickHouse cluster, and the database permission change was rolling out gradually, the system entered this incredibly confusing state.
What did that look like for the engineers on the ground watching the dashboards?
A total nightmare. A good configuration file might sometimes propagate, across parts of the network, and you'd see these brief periods of recovery. Then, 5 minutes later, a ClickHouse machine that had just gotten the permission change would generate a new poison configuration file, and all the proxy nodes that got it would immediately crash again. This constant fluctuation up, down, made it almost impossible to do a traditional root cause analysis.
And I remember the sources mentioning that this chaotic state actually led them down the wrong path at first.
That's right. The instability looked a lot like a sophisticated attack. The sources confirmed that the fluctuating traffic led the teams to initially suspect a high-volume DDoS attack, specifically mentioning known patterns like the Iserduos attacks. And that consumed valuable time in the beginning because they were looking for an external enemy instead of an internal configuration flag.
That complication, the system failure, mimicking a known threat, it really highlights how hard it is to manage entropy in a distributed system.
Okay, so once that core proxy system starts crashing, the failure just ripples outward. What was the most immediate and widespread symptom users saw?
The universal symptom was HTTP 5XX status codes, specifically internal server errors. That's what you get when the core proxy, the thing that's supposed to handle the basic HTTP handshake and routing, just fails to process the request. So millions of users trying to get to websites protected by Cloudflare were just met with a wall of error pages.
And what's fascinating is that the failure itself wasn't uniform because they were in the middle of this big migration to a new proxy engine, FL2. How did that add to the confusion?
Oh, it added a huge layer of confusion. The traffic that was still on the newer FL2 proxy, that's what experienced the immediate Rust panic and the 5XX errors. That system just crashed hard. But the older FL proxy engine was built differently. It didn't crash. Instead, it suffered this critical internal logic failure in how it processed the poison file. So the older system stayed alive, but it started spitting out useless security data.
Exactly. The FL proxy started generating invalid bot scores. Instead of crashing, it processed that corrupted feature file in a way that resulted in all traffic getting a bot score of 0. Now, if a customer was relying on a security rule to automatically block traffic with a bot score of 0, which is a common setup to block spam bots, they suddenly started blocking huge volumes of legitimate human users.
Wow, that's a perfect example of a distributed system failure. One system, FL2, fails by dying completely. The other, FL-Bell, fails by going functionally insane, all from the same bad data.
It really shows the complexity of managing these large-scale software migrations. You have different code bases reacting to the same bad input in fundamentally different but equally devastating ways.
Let's talk about the edge services. Workers KV is a hugely popular product, this high-speed key-value store. How did that suffer?
Workers KV saw severely elevated 5 McX errors. The key is the architecture. Workers KV requests depend heavily on the core proxy system acting as the front-end gateway. So since the core proxy was failing, the requests to Workers KV failed before they could even hit the storage layer. In fact, the initial symptom that the Cloudflare team was really focused on, from about 11.32 to 13.05 UTC, was the rapid degradation of response rates for Workers KV. It was the canary in the coal mine.
And then there's the administrative side of it, locking out the very people who needed to fix the problem.
This is maybe the cruelest irony of the whole thing. The failure spread right to their user authentication layer. Cloudflare uses Turnstile, their human verification system, on their own login pages. And during the outage, Turnstile failed to load entirely. And since Turnstile was unavailable, the logic that's supposed to prevent bots from logging in also prevented human users, including their own ops team, from logging into the Cloudflare dashboard to fix the issue.
So if you were already logged in, you were fine. But if you were scrambling to respond to the crisis, you were locked out by your own security system.
Precisely. A total catch-22 of self-denial. And it was similar for their Cloudflare Access product, which controls access to customer internal apps. It saw widespread authentication failures. Existing sessions were okay, but any new login attempts failed, and you'd just get an error page.
And that secondary failure loop, the observability systems making the CPU usage worse. That's the kind of detail that only comes out in a post-mortem. How did the tools meant to help actually hurt them?
The systems were designed to be, aggressive in collecting data when errors happen. So as the core proxy started panicking and throwing all these 5xx errors, the debugging and observability systems automatically kicked into overdrive. They started consuming these huge, unexpected amounts of CPU across the network to enrich the errors with debugging info like stack traces and memory dumps.
So every server that crashed immediately started burning excessive CPU trying to document its own death.
Exactly. And this secondary resource consumption led to significant latency increases across the entire network. The system meant to diagnose the failure, inadvertently starved the remaining functional systems of the CPU cycles they needed.
And what about their other specific security products, like email?
Even services that kept operating, like email security, suffered. Processing continued, but the system temporarily lost access to a critical external IP reputation source. So this slightly degraded their spam detection and blocked some new domain age detections. More spam might have slipped through. And some automated actions like auto-move rules failed intermittently and had to be cleaned up later.
And then there was that bizarre external coincidence that just confirmed the team's early suspicion of an attack.
Right. As if the internal chaos wasn't enough, their external Cloudflare status page, which is meticulously hosted outside of the Cloudflare network to ensure it stays up, briefly went offline during the incident. And that optical failure, the status page itself winking out, combined with the oscillating crashes, it just strongly reinforced the internal fear that they were facing a coordinated multi-system cyber attack. It was a crazy coincidence.
But at the end of the day, it was still just that one rogue configuration file.
That's right.
So the moment the investigation finally shifted from looking for an external attacker to looking at an internal configuration failure, the clock started ticking on the recovery.
Yeah.
Walk us through that rapid timeline.
The impact started at 11.28 UTC. The crucial identification, the aha moment, came a bit over an hour and a half later, around 13.05 UTC. That's when the team finally narrowed the source down to the bot management configuration file.
So finding that one needle in the haystack took a pretty significant effort. What was the fastest way out once they found it?
The fastest path was surgical. They had to stop the bad file from propagating and replace it with a known good version. So at 13.37 UTC, they started focused work on rolling back that bot management configuration file to a version they knew was good before the 11.05 database change.
And then stop the bleeding.
Yeah, exactly. The next milestone was stopping the self-inflicted damage. At 14.24 UTC, engineers successfully halted the ClickHouse cluster from creating and propagating new bad configuration files. That sealed the wound.
And then the main moment of relief, when the network actually started stabilizing.
That came at 14.30 UTC, just 6 minutes after they stopped generating the bad files. A previously verified known good configuration file was manually inserted into the distribution queue and deployed globally. Almost immediately, downstream services saw a sharp reduction in 5NAX errors, and core traffic started flowing again.
That's a really rapid response once you know the root cause. But full recovery, that takes longer. When was the final all clear?
The system had entered so many different failed states.
Huh.
You know, the workers' KV degradation, the access lockout, the overloaded CPUs, that the long tail of recovery was substantial. The incident wasn't declared fully over until 17.06 UTC. That's nearly 4 hours after the main fix was applied, once they confirmed all downstream services were restarted and error rates were back to normal.
A 5-hour global outage that began with a single database permission change. The lessons learned here must have been immediate and pretty stark. What were the key commitments they made?
They identified 4 major areas for reinforcement. First, strengthening configuration protection. They committed to adding multiple new layers of validation to make sure future configuration files can't propagate if they violate integrity rules, like exceeding a max feature count.
Makes sense.
Second, improving their kill switch controls. They promised to refine their tools so they can rapidly shut down a failing service faster than a bad configuration change can propagate globally.
Okay, a faster off switch.
Third was refining proxy error handling. This is huge for systems written in languages like Rust. The goal is that a violation like this shouldn't trigger an unrecoverable panic, but instead a more graceful degradation, so the system fails safely, not catastrophically.
Right.
And finally, addressing that secondary injury, preventing the diagnostic tools from overwhelming the system. They committed to re-engineering their observability systems to cap their own CPU consumption.
So the act of diagnosing a failure doesn't contribute to the failure itself.
Oh,
It's a comprehensive response to what was clearly a multi-layered failure that all stemmed from one tiny point of origin. It's just the fragility is inherent in these complex systems.
And that fragility leads us directly to the philosophical opposite. If bad configuration data can crash the internet, we have to talk about the absolute foundation of good data. True, unpredictable randomness. This is where Cloudflare really pivots from network engineer to cryptographic pioneer.
The irony is pretty profound. They need total incorruptible security for their core function, TLS encryption, and all of that relies on a secure random seed. Explain that relationship for us between a CSPRNG and true randomness.
Okay, so think of a CSPRNG, a cryptographically secure pseudorandom number generator, as a high-performance engine. It's designed to produce this infinite complex stream of numbers that are mathematically impossible to tell apart from true randomness. But even the best engine needs perfect fuel. And that fuel is the initial seed, which has to come from a source of genuine physical entropy. If that seed is predictable or if the source is biased, the entire cryptographic guarantee, the confidentiality and authenticity of your TLS connection, it just collapses.
And historically, servers would rely on local entropy, right? Like the precise timing of mouse movements or network packet arrivals.
Exactly. But as systems become virtualized and more deterministic, those sources become less reliable or potentially vulnerable to prediction. So Cloudflare, dealing with the security of a huge portion of the web, decided they needed to hedge against those local entropy sources being compromised. They needed an external, unimpeachable, physical source of chaos.
And that search led them to the now legendary Lavaran system back in 2017. This is the part that always feels like high-tech performance art.
It is delightful technological absurdity. The original source was a literal wall of lava lamps in their San Francisco office.
The lava lamps.
Just lava lamps. They're capturing pure, physical, chaotic flow. At regular intervals, a camera takes a picture of the flowing wax. That image is then processed. It's hashed into a compact set of genuinely random bytes.
And how do they use those bytes?
They're fed into something called a key derivation function, or KDF. The KDF mixes the random bytes from the lava lamps with local system randomness and the previous cryptographic seed to produce a new, perfectly fresh seed for the CSPRNG. It's constantly refueling the engine with physical unpredictability.
And what's fascinating, as the sources point out, is that the system benefits not just from the visible chaos of the wax, but from the hardware itself.
That's the beautiful, subtle detail. Serendipitous noise. Image sensors are inherently noisy. They produce these small, unpredictable fluctuations even when they're looking at a perfectly static scene or even with the lens cap on. This inherent imperfection in the electronics adds another layer of physical entropy. The chaotic movement of the lamps is enhanced by the statistical noise of the camera. It's all spice added to the entropy pool mix.
And that philosophy of diversifying their entropy sources didn't stop with lava lamps. They've expanded the chaos portfolio across their global offices. Tell us about the double pendulums in London.
So the London office introduced a source of what mathematicians call deterministic chaos. A double pendulum is, well, it's two pendulums attached end to end. And while the system is governed by classical physics, it's deterministic. Its motion is exquisitely sensitive to initial conditions. A tiny, tiny difference in how you start the swing results in these wildly divergent, non-repeating paths. It is mesmerizingly unique every single time.
And unlike the lava lamps, which are internally powered, the pendulums also rely on the environment around them.
Precisely. The camera captures not just the movement, but the changing light conditions and shadows throughout the day. The position of the sun, indoor lighting, all of it is captured as unique input and fed into the entropy pool.
And then in Austin, they have the translucent rainbow mobiles.
Right, and the mobiles capture chaos driven by atmospheric and human elements. They twirl in response to the environment, they're sensitive to the HVAC system cycling on, a door opening down the hall, and they reflect and refract light, casting these colored, changing patterns that are captured. It's a really low-tech, high-impact source of entropy based on just ambient office life.
So once they have this stream of cryptographically validated chaos, how do developers actually use it? You mentioned there are private and public flavors of randomness.
Yes. The primary use is private randomness. This is used internally for generating secrets, things like cryptographic keys, session keys, user IDs, secure passwords, things that must remain secret forever. And because Lavarand is constantly refreshing the system's entropy pools, developers on, say, a Cloudflare worker can tap into this high-quality stream through standard tools like the Web Crypto API.
Okay, and the other side is public randomness.
Public randomness is non-secret. It's for unpredictable and unbiased values that are made available to everyone once they're published, like a globally trusted coin flip or a lottery number. The challenge for public randomness isn't generating it, it's trustworthiness. A global consumer needs to be absolutely sure that the value was produced faithfully and wasn't manipulated.
And this is a huge distinction because as the source material highlights, if you only trust one authority, that authority becomes a single point of failure, like the lottery employee who rigged the RNG system.
That is the precise trust problem that the DRAND network, pronounced DRAND, was created to solve. Recognizing that relying on a single entity creates a vulnerability, Cloudflare joined forces with 7 other independent organizations back in 2019 to form the League of Entropy.
So Cloudflare contributes the chaos from their lava lamps and pendulums to this joint distributed pool. And how has this League of Entropy grown?
It's matured significantly. It now includes 18 independent organizations across 4 continents, universities, research groups, other infrastructure providers. DRAND is no longer an experiment. It's a reliable, production-ready internet service. It's being used for secure file storage, transparent gaming, and advanced cryptography.
So what are the 2 core properties that transform this joint pool into something globally trustworthy?
Decentralization and verifiability. Decentralization ensures that no single entity or even a small group can bias the randomness. Verifiability is the revolutionary part. Anyone, anywhere, can check that the published random values were produced correctly according to the strict cryptographic protocol.
And this verifiability is mathematically guaranteed, right? It just needs a certain number of participants, to be honest.
That's the magic number. It requires participation from a threshold, usually more than 50% of the network's participants. If 10 out of 18 members cooperate honestly, the system works perfectly, even if the other 8 are malicious or just offline.
Okay, let's get into the mechanics here. This is where the deep dive happens. How do 18 independent nodes generate a shared secret key without ever actually revealing the key itself?
That starts with distributed key generation, or DKG. It's a complex but secure technique where, instead of one entity creating the master key and distributing shares, all the nodes cooperate to simultaneously construct a common, shared, distributed group key.
So no one ever knows the master key. They only know their own little piece of it.
Exactly. And once that distributed group key is established, the randomness is generated using threshold signatures, specifically the BLS signature scheme.
Explain how a signature becomes the randomness.
So the system operates in rounds. The QuickNet beacon, for example, produces a new round of randomness every 3 seconds. To generate the randomness for, say, round 500, a threshold of nodes must cooperate. Each node uses its private share of the key to create a partial signature over an agreed-upon message, which is usually just the round number. Once enough of those partial signatures are collected, they can be combined into a single, verifiable group signature. And that group signature is the unpredictable, unbiased, random value for that round.
The genius is that the final output is unpredictable until that threshold of signatures is combined. And because it's a BLS signature, anyone with the public key can instantly verify that it was produced legitimately.
That's the core innovation. You're verifying math, not trusting a single corporation. And this led to a key improvement in usability, the shift from chained to unchained randomness.
Why did they start with chained and why did they move away from it?
They started with chained randomness because some cryptographic standards like from NIST demand it. In that mode, the message for round N included the signature from round N1. It's great for security, but terrible for performance. To fully validate round 500, you'd have to reconstruct the entire history all the way back to round 1.
Which sounds computationally impossible for most users.
It was. So the DRAN team introduced unchained randomness in 2022. In this simpler mode, the message they sign is just the predictable round number itself. So a user only needs the current round number and the public key to validate the randomness. It's instantaneous.
And this change unlocked the true killer app for the DRAN network.
Absolutely. The ability to implement time-lock encryption or time-release cryptography. This is encryption designed so that a secret message cannot be decrypted until a specific predetermined time has passed, enforced by the external reality of the DRAN network.
How can they guarantee that time delay using cryptographic signatures?
The mechanism is really elegant. Each round number corresponds to a predictable timestamp. If you want to release a secret on, say, December 1st, 2026, you figure out the exact DRAN round number that will occur at that second. You then encrypt your message, or more practically, a secret key for the actual message, using the public key that's associated with that future round.
So the ciphertext is locked to a future public key that hasn't even been generated yet.
Correct. The message is impossible to decrypt until the DRAN network reaches that specific round. Once the League of Entropy nodes cooperate to generate the verifiable group signature for that round, that signature is publicly revealed. And that signature acts as the decryption key, allowing anyone with the ciphertext to instantly unlock the message.
That is staggering. They're using global verified physical chaos and distributed consensus to eliminate the need for a trusted third party, like a lawyer or an escrow service.
It creates an unbreakable cryptographic deadline, enforced by a global network that's constantly fed by lava lamps and double pendulums. It's the ultimate contrast to the fragility we saw earlier.
That contrast is essential. We've discussed the catastrophic, unexpected failure, and then these high-tech philosophical solutions. Now, let's turn to the sources on operational reality. The constant, grinding effort required to run a massive global network.
Right, the postmortems grab the headlines, but the status pages detailing scheduled maintenance, that tells the true story of operational resilience. This isn't just fixing things when they break, it's proactively replacing hardware, updating firmware, and migrating infrastructure, all while trying to ensure no downtime.
And if we look at the calendar around November 20th, 2025, the density of activity is just staggering, particularly in North and South America.
Oh, the concentration of maintenance is huge. On that single day, multiple key data centers were listed as in progress.
Oh.
You see major hubs like IAD in Ashburn, PHL,
Philly, yeah.
MIA in Miami, GYE in Guayaquil, Ecuador, and EWR in Newark. This is a heavy lift affecting latency pathways across the entire Western Hemisphere.
And some of those maintenance windows are really significant.
Yeah, the duration is notable. The window in Newark was scheduled to run from 07.00 to 19.00 UTC. That's a full 12-hour block of coordinated network work.
And looking ahead over the next few days, it's clear this is a continuous global reality.
The forward planning demonstrates that. In the Americas, you've got San Jose, Dallas, Chicago, Omaha, Calgary, all on the 20th. And major hubs like IAD, EWR, and Atlanta have repeat maintenance days, which suggests major hardware refreshes are going on.
And the tempo in Asia and Oceania is just as demanding.
We see Perth, Hong Kong, Singapore, and Kuala Lumpur on the 20th. Mumbai and Karachi extend late into the 21st. Osaka has maintenance on the 21st and 24th. Then in Europe, you've got Vilnius, Frankfurt, Stockholm, Bratislava, Warsaw. The list just goes on.
That entire list is essential because it shows that even the most advanced networking company has to deal with the physical world. Aging hardware, power, logistics.
It's the constant fight against physical entropy. Every server, every fiber optic cable eventually needs replacing.
Which brings us to the critical impact warning they provide for all this scheduled work. What do they tell their big enterprise customers to expect?
The warnings are very specific. First, for standard end users, traffic will be rerouted. There's a possibility of a slight temporary increase in latency, but it should be pretty seamless. Second, and much more impactful for enterprise clients, is the warning about their interconnects. Network interfaces for P&I and C&I customers may become temporarily unavailable.
And we should unpack P&I and C&I. These aren't just casual connections.
Not at all. P&I and C&I are the deep, direct physical links that large customers, banks, software companies use to connect their private networks directly to Cloudflare's backbone. They're the highest tier of service.
So when one of those interfaces goes down for a 12-hour window, what does that mean for the customer?
It means that customer has to have robust traffic failover planning in place. They have to assume that link is dead for the duration and immediately shift their traffic to alternate redundant interfaces in other regions. It's a mandatory high-stakes operational procedure for them.
That level of detail really highlights the logistical burden. And the sources also give us a glimpse into the smaller, non-catastrophic fires they're fighting every day.
Yeah, the recent incident examples show the diversity of challenges. Just before the big outage on November 19th, there were issues with specific products like Magic Wand routing. That required a specialized team to investigate.
And other high-level networking protocols breaking.
Exactly. On the same day, there was a separate issue with IPsec tunnels in Magic Transit and Magic Wand. These are complex, secure tunneling protocols that can break in their own unique ways.
And even their AI services aren't immune to entropy.
We saw that too. Workers' AI had a high error rate specifically for the Llama language model. Separately, Durable Objects, a storage mechanism, saw elevated overload errors in Western North America. This daily log just shows a constant global battle against both physical and digital entropy. The November 18th outage was an anomaly in its scale, but the daily operational tempo is a nonstop war against complexity.
This journey has been such a study in contrast. On one hand, you have the profound fragility of these massively scaled systems. A single line of code, meant to improve security, opens up a schema view, doubles a query's output, triggers a memory limit, causes a system-wide Rust panic, and takes down the internet's front door for hours.
It was the digital butterfly effect operating at maximum velocity. And on the other hand, you have these extraordinary, almost beautiful measures taken to secure the system. They're hedging against the randomness of the digital world by tapping into true physical chaos, the flow of lava lamps in San Francisco, the chaotic swing of double pendulums in London, the ambient movement of mobiles in Austin.
And this physical chaos is then aggregated into this high-tech solution, the decentralized DRAN network. It uses cryptographic consensus to provide verifiable public randomness, which is then used for the most cutting-edge security, like guaranteed time lock encryption.
It's humbling, the level of engineering sophistication required to manage a system that is simultaneously so fragile and so robust.
And if you look at those maintenance status pages filled with UTC coordinates and P&I warnings, you realize that those aren't just dry reports. They are the active, continuous diaries of a system relentlessly managing chaos, both physical and digital.
The operational reality is that the internet we all rely on is constantly being mended, reinforced, and protected by these highly esoteric technology systems that sometimes save us, and sometimes, ironically, nearly kill us.
So we saw the internet crash due to a piece of bad data, but we also saw security built on the highest quality of good data, true randomness, from high-tech office decoration. That dichotomy leads us to our final thought for you to explore on your own.
We discussed how the DRAND network introduced unchained randomness, allowing secrets to be cryptographically locked to a future predictable time. So if secrets can now be guaranteed a forced public revelation at a specific date, what unforeseen social, legal, or political consequences might arise from the ability to eliminate the trusted agent entirely and use verifiable public randomness to guarantee the time release of sensitive information? Consider how that could change whistleblowing or inheritance or even political transparency.
A profound thought. Something to mull over until our next deep dive. Thanks for listening.